Last time I left you with a cliffhanger, right? So we better try to resolve that. That was the two envelope problem. So remind you what the problem is. It's very simple to state, but not so easy to resolve. So the problem is just we have two envelopes, envelope 1, envelope 2. They look identical, and suppose there are X dollars in here and Y dollars in here, and you don't know anything at all about X and Y. This are random variables right now. And all you know is that one envelope has twice as much money as the other. So they each have a check for some amount of money, and one is double the other, but you have no information other than that. Twice as much as the other. Okay. So the argument last time was, let's say you get to pick one. So let's say you pick this one, and if this one's X, and you don't know what X is unless you open it, but you do know that the other one is either 2X or X over 2. And if you average 2X and X over 2, you get a number bigger than X, which suggests that this one is better. But you could have applied the same argument to this one. If this one's Y, the other one's 2Y or 1/2 Y. If you average 2Y and 1/2 Y, you get a number bigger than Y. So, all right, so let's actually write that out kind of formally as an argument. So basically there are two competing arguments here. Argument 1 is simply that E of Y equals E of X by symmetry. So if you were given some piece of information that, like, the person who put the money in the envelopes is left-handed, and left-handed people subconsciously want to put more money on the left or something like that, then you'd have an asymmetry in the problem. But there was no asymmetry given. The way it was stated is just, you know, there's no difference that the left envelope should have more or the right one, so it's a symmetrical situation. So it's kind of hard to argue against symmetry here, right? There is no asymmetry in the statement of the problem, so if somehow the envelope on the left were better, where would that have come from? That doesn't make sense. Okay, so that's a pretty strong argument. But let's look at argument 2, which also seems pretty strong. Argument 2 is to condition. You say, how do we compute expectation? Just like, well, you know, when we had a probability we didn't know, we want a condition on the thing we wished that we knew. So this is just the law of total probability, except the expectation version. We're going to condition on whether, you know, either Y equals 2X or Y equals 1/2 X. So we could just write it this way. E of Y given Y equals 2X times the probability that Y equals 2X plus E of Y given Y equals 1/2 X times the probability that Y equals 1/2 X. So I mean, that's just, you know, a fact about expectation that you condition, and the proof of this is basically just use the law of total probability, and that's true. So it's hard to argue with that. Let's compute this. So the argument goes, E of Y given Y equals 2X, well then we know Y equals 2X, so we're just going to replace that by E of 2X. By symmetry, it's equally likely that Y equals 2X and Y equals 1/2 X, so that's just 1/2, plus, in this case, Y is X over 2, so we're going to get E of X over 2, probability, well, that's 1/2 again. And if you simplify this, you know, you can take out the 2, take out the 1/2, simplify, you get 5/4 E of X. All right, so then the question is how to resolve this. Well, first of all, is there any case in which both of these statements could be true? Someone said 0. Well, kind of, yeah, both envelopes have $0, then that would be okay. So let's assume there is a positive non-zero amount of money in both envelopes. Are there any other case? Infinity. Well, infinity equals infinity. Infinity equals 5/4 infinity. So one way out of it could be to say, well, on average, there's an infinite amount of money, and that, then you're pretty happy, right? But there are not many, kind of like the St. Petersburg paradox, where the expected value is infinity. But there are not many real-world scenarios that you could think of probably where your expected value of how much you'll make is infinity dollars. So so let's assume that these numbers are not 0 or infinity. In that case, this is just a direct contradiction, meaning that one of these two things must be wrong. Well, symmetry, I can't find any way to argue against the symmetry here. So this has to be right. The symmetry takes precedence. So let's try to see what's wrong with argument 2. Well, actually, this is one of the most common and troublesome mistakes with conditioning, is to kind of like use the information and then forget about it. That is, look at what we did here. We plugged in the information y equals 2x, but then the condition went away. What's the justification for that? There is none. It just kind of looked good to say that, but there's no justification. So actually, this step is wrong. So that's not actually it's not equal. What we should have written was, it's perfectly valid to plug in the 2x. Well, let's write the corrected version. It's perfectly valid to plug in 2x, but that doesn't mean we can forget that we know y equals 2x. So it's 2x given y equals 2x. And similarly over here, we can plug in the information, but it doesn't mean we're not conditioning on it anymore. So we can do that, but we still have to then evaluate this conditional expectation, right? We can't just say that we can forget this information here. In fact, there's no more justification for forgetting this information here than there would be up here, right? You just can't say that. So actually, what we just showed is that essentially e of let's say e of x given y equals 2x is not equal to e of, well, let's do it this way. E of y given y equals 2x is not equal to e of 2x. So what's going on there is, I like to think of this in terms of indicator random variables. So let's just let I be the indicator random variable. I is the indicator of which envelope has more money. So we could say I is 1 if y equals 2x and 0 otherwise, or you could define it the other way around. That's the event that says that the envelope on the right has twice as much money as the one on the left. Okay, so we have an indicator for that. Then essentially what we just showed is that x and I are dependent. We can either talk about x and I or talk about y and I. They're dependent. And that seems surprising at first. So if you think, well, let's think about what that means. It says that if you got to observe x, then somehow that gives information about I. So let's say, so now we get to think more about the case, what happens if you actually get to open the envelope on the left, and you see, $100 there. So you know the other one is 50 or 200, but the question is whether that changes your probabilities for I. That is the other one 200 or 50? It's saying it's not 50-50 anymore, which seems a little strange because you're not given any information kind of about the scale of the problem. So let's say you open envelope on the left and there's $1 trillion there. Well, probably you're really happy, but is $1 trillion a big number or a small number? Well, it's a lot of money, but in the grand scheme of things, compared to the entire, real line from 0 to infinity, the trillion is minuscule, right? $1 trillion is nothing compared to other numbers I could name if I wanted. So when you see that $1 trillion, Does that give you information that makes you think that the other one is probably only half a trillion because a trillion is big? But what's a trillion, right? It's nothing compared to 2 to the 2 to the 2 to the trillion or something like that. But if you would observe that, then that's nothing compared to other numbers I could name. So it seems surprising that they're dependent, but essentially we just proved that they have to be dependent if the expected values are finite. And there's a strategic practice that's related to this too, which says that you can look at the problem if you haven't already, but just to tell you what the result of that problem is, which is also surprising, it also is a two-envelope problem, but in that problem, it just assumes that there's two amounts of money, two positive amounts of money. It's not assumed that one is double the other. And the problem is to come up with a strategy that gives you, guaranteed to give you better than a 50% chance of getting the envelope with more money. That is, you get to observe one, and then you choose whether to switch. You can guarantee that your probability of success is strictly greater than 1/2, which again, at first sounds impossible, because if it's $1 trillion, should you switch or not? But it says in a certain sense that actually you can make a measure of, is $1 trillion a big number or a small number? And the strategy used in that problem is to generate your own random threshold. That is, you generate some value t, let's say from an exponential distribution, but it doesn't have to be. You could pick some other distribution. You generate your own threshold value, and then you say you're happy if you got more than t, and you're unhappy if you got less than t, and that gives you a better than 50% chance of success. All right. So anyway, that's the two-envelope problem. There's many different articles and debates about this, and some people try to take Bayesian approaches to resolving this and so on, but I think that's fairly unnecessary. I think that the key blunder is just in this step, and this is kind of a strange problem, but this mistake comes up in a lot of other contexts as well, so it's worth thinking carefully about. That is, we plugged in the information, but that doesn't mean we can then get rid of the information. The only time when we can get rid of the stuff we're conditioning on is when we know we have independence. And here there was no justification for independence, and in fact, x and I, or y and I, can't be independent, which is not obvious. It's not obvious that they're not independent, but on the other hand, you can't just say they're independent without proving it, and if you try to prove it, you'll find they actually are not independent here. So that's what's going on with that problem. All right, so let's do another example of conditional expectation with coin flipping problem. So, okay, so I'll call this one patterns in coin flips. Okay, so assume we have a fair coin, and you have a related homework problem where the coin may be biased. But right now we're assuming we have a fair coin, and we do repeated fair coin flips. And we're waiting for a certain pattern, okay? So we're gonna wait until, we wanna know how long, how many flips until we observe the pattern, heads followed by tails. So I'll just call that HT. That is, keep flipping the coin, and eventually you will observe heads immediately followed by tails, right? That particular pattern will eventually show up. You want to know how many flips does that take, including the H and the T there. Okay, that's a natural question we could ask. Similarly, we could ask how many flips until HH. That is, how long do you have to flip the coin until the coin lands heads twice in a row? Okay, so let's find the average. So let's call that. I'll just call it WHT and WHH. By WHT, I just mean the random variable representing how many flips does it, imagine this long sequence of coin flips, and how far into the sequence do you have to get until you see HT for the first time, how far until you see HH for the first time. Those are both random variables. But right now we're talking about expectation, so the question is to find the average So our problem is to find the expected values of these two waiting time. I'm using W for waiting time. Expected value, how long you have to wait for these patterns. Okay? Well, so we'll solve both of these. But before we actually solve them, let's try to think more qualitatively about whether there's an inequality or equality here. Okay, so we know that there's only three possibilities. Either this number is bigger than this number, or it's equal, or this is less than this. Okay? So why don't you take a few seconds to think intuitively about whether you think they're equal or one is bigger, and if so, which one is bigger. Then we'll vote. Then we'll see, okay? So there's three possibilities, right? So think about which one you think is true. Okay, so how many of you think this is greater than this? Raise your hand if you think this is greater than this. Okay, and how many of you think this equals this? Okay, and how many of you think this is greater than this? Okay, so the dominant answer is equality, and then it's roughly equal numbers saying this greater than this, or this greater than this. Okay, well, the answer is this one equals 4, and this one equals 6, 50% bigger. But you might say, well, by symmetry, don't they have to be the same thing? That would be a false use of symmetry. Symmetry would tell us that, if we ask the same question, let's do a little symmetry argument over here. Symmetry would say expected value of WTT equals expected value of WHH. That has to be true by symmetry. Because, the coin, it says heads on one side, tails on the other, but you could have, relabeled it. It's the same problem, again, just with a different labeling. So that's symmetry, that I'm interchanging heads and tails. Similarly, we know that E of WHT equals E of WTH. But neither of these tells us that these are equal. It doesn't tell us that they're not equal. It's just you can't just say by symmetry, because you have to swap heads and tails everywhere, and those are different things. All right, so let's do the calculation. Then I'll talk a little more about the intuition for why is this bigger than this. But let's just calculate it first. Okay, so first let's do E of WHT. So a nice way to think about it, we don't actually need conditional expectation for this. A nice way to think about this problem is to just imagine a sequence of tosses. Maybe starts out tails, 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 tails. Eventually, the coin will land heads, right? Now, once this has happened, you can see we've made partial progress, right? Because now, well, if the next flip is tails, then we're done. But if not, that's okay. Heads, heads, heads. Eventually, it'll be tails. So then we're done, right? Then we got it. So just drawing, a few examples like that, make up your own little sequences to make it concrete. Then you'll see what's going on here, which is that all we have to do is wait for the first time the coin lands heads. Let's call that W1. So that could be the first flip, but it could be however long it takes, till the first head. And then, after that point, how long do you have to wait additionally for the first tails? Let's call that W2. So no matter what happens, I can always split it up as a W1 and a W2, right? Time to the first heads, time to the first tail after the first heads, right? Well, okay. Those are independent of each other because the coin is memoryless, but even if they were not independent, we could still apply linearity and just say this is E of W1 plus E of W2 equals 2 plus 2 equals 4, since the W is basically a geometric. The only thing we have to be careful about is that we define the geometric to not include the success. So actually Wj minus 1 with our convention is geometric 1/2. Right? It's just the waiting time for success, where here we're defining success to be this heads, and here we're defining it to be this tails. Okay? So geometric 1/2. This has expected value 1. 1 plus 1 is 2. So each of these, on average, it takes 2 flips to get to this stage, 2 more flips to get to this stage. 2 plus 2 is 4, linearity. Okay, so let's try to do the same thing with heads and see why that doesn't give us the same thing there. All right, so now we're going to do E of W of HH. And again, it just really helps to, for concreteness, draw some little, examples. So again, maybe the sequence starts out tails 3 times, 4 times, like here. Eventually the coin lands heads. Now at this point, so we could still call that W1 if we want, but at this point, either of two things can happen. Either the next flip is heads, then we're done, we got it. But if the next toss is tails, we have no partial progress anymore. That means that in this scenario, these tosses were all wasted, right? They do nothing for us. Then the thing just restarts, right? I mean, it took 6 tosses to get to this point, but we're starting again with the exact same problem we had, right? No partial progress. In this case, we have partial progress because once you get this heads for the first time, then you're halfway there, essentially, right? That's the key distinction. All right, so here we have to be more careful, because in this case, all these tosses are gone, and then we just start over again. Okay, so now we're going to use conditional expectation to compute this. So it's kind of like gambler's ruin type of thing, where it can condition on the first toss. So this is E of WHH given. You can make up some notation if you want, but I'll just write it. First toss is heads times 1/2 plus, that's the probability that the first toss is heads, plus expected value WHH given first toss is tails times 1/2. Just conditioning on the two cases that this first toss is either heads or tails. And now let's expand it out further. This one we need some space for, probably. This one, the second term is actually easier here. Okay, so I want to compute this thing. I want the expected value WHH given that the first toss is tails. Okay? That first toss is tails. What does that say? It says the first toss is tails. That cost us 1 toss. Tossed the coin once, coin was tails. Okay, then it's the same problem again, right? Exact same problem. So that's just E of WHH again. We're going to try to solve for it in terms of itself, which sounds circular, but then we have an equation. We can just solve that equation for E of WHH. Okay, so that was the first toss, was a waste, and then it's the same problem again. Now for this first term, first toss is heads. We have to further subdivide it into 2 cases based on the second toss. So here when we're doing this conditional expectation, it means we're working within a world where we now know the first toss is heads. That's the information we have. Now we look at the second toss. Second toss, if the second toss is also heads, then that means the first 2 tosses were HH, and then we're done, and it only took 2 flips, and that has probability 1/2. But with probability 1/2 within this case, the second toss is tails. In that case, the sequence started out HT, which does nothing for us, right? That means it's a waste of 2 tosses, and then it's the same problem again. Right? 2 tosses from heads, tails, and then it's the same problem. It reset again to the same problem. All right, so now we have an equation for E of WHH in terms of itself. So just multiply the 2 times 1/2 is 1, move things around, and you get that the expected value is 6. Which you can also check just by plugging in 6 here. This is 5/2 plus 7/2 is 12/2 is 6. So that works. All right. Okay. So that seems a little strange. And to kind of explain a little bit of the intuition here, let's imagine drawing like a long sequence of coin tosses and look at where did the HHs appear and where did the HTs appear. So maybe it looks like TT. H, 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 T, blah, 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 blah. And then somewhere later on, there's an H, H, and a T, and it looks like. You can make up your own sequence. I'm just going to try to illustrate kind of what's the big picture of why this is true. In other words, the question, I guess, is why doesn't this contradict the fact that since it's a fair coin, if we flip the coin twice, then all 4 possibilities are equally likely. So if I'm only looking at 2 particular positions, let's say here and here, it's equally likely that this will be HH as for it to be HT. Those are both 1/4. Okay, so I think that's where the intuition comes from that should be the same. If you look at any 2 positions, it's equally likely. But we're not just looking at 2 positions, we're looking at the entire sequence. And what happens is that with the HHs, sometimes you'll get like 3 heads in a row. Sometimes you'll get 5 heads in a row. If you have 3 in a row, then that means there's an HH there and an HH there. They're nested. So if we had like 5 H's in a row, which will happen more often than most people would expect, because coincidences happen a lot. Then look at all these HHs in the with those 5 in a row. Try to do the same thing with HT. You can't, right? It doesn't nest inside itself in the same way. So that means that when you get the HHs, they're kind of clumped together. But on the other hand, you have the same expected total number of appearances of that. So since the HHs are more clumped, they appear in clumps, those clumps must be further apart. That's what's going on. Okay. And if you think this is just kind of like a curiosity of coin flipping, this kind of problem actually has important applications in genetics. In genetics, we would not be looking at sequences of heads and tails, but we would look at a DNA sequence, which is a sequence that's drawn from the alphabet A, C, T, G. And a lot of times in genetics these days, people want to say like, study certain patterns, right? They call motifs, where the pattern appear in the DNA sequence, and you get similar problems. And while I'm mentioning this, I'll recommend a TED talk. Peter Donnelly is a statistician who works on genetics, and if you go to his, I don't know if you've seen any of the TED talks, but if you go to TED.com and look for Peter Donnelly's talk, he mentioned some interesting courtroom examples, statistics and probably in the courtroom, and he also talks about an example similar to this. It's quite a nice talk. Okay, so that's waiting for certain sequences. You can extend this in various directions. Like this was already, a fair amount of work, not too bad. You could also ask more complicated questions, like longer sequences and things like that. And there are a lot of other methods that could be used for more complicated sequences. But the basic method is just conditioning. So you can see that conditional expectation, just like in the Gambler's Ruin, let us simplify kind of this complicated problem, break it up into simpler pieces by conditioning on the first 2. Essentially what we did was to condition on the first 2 tosses. Another way to do that, but I sort of did it in 2 steps. We could have also done this just by, at the very beginning, breaking it up into 4 cases based on the first two tosses. That might have been even easier, but anyway, I did the 2-step way. Okay, so that's a basic idea of conditional expectation. And I guess to just state it a little bit more, some of the general properties of conditional expectation and would be useful. And also, we're leading into conditioning on a random variable. Like this whole week is about conditional expectation. So far, we've been doing conditional expectation where we condition on an event, okay? But what we're gonna get to is what does it mean to condition on a random variable? And it's important to, they're very, very closely related, but if you mix them up, then it can be bad. Okay, so what, let's see. So we have this thing that's like e of y given x equals x. I just want to make sure everyone is completely clear on what this means both intuitively and mathematically. What does this expression actually mean? Well, you know, I've said over and over again that big X equals little x is an event, right? I mean, I'm assuming capital X and Y are random variables. Little x is a number. We're conditioning on that event. And as I've been saying, all that means to do is use the same definition of expectation, except make it conditional. That's why it's called conditional expectation. Okay, so at this point, you know, you should all be able to just write down the definition that this is for y discrete, and we'll write down the continuous case too. Okay, so in the discrete case, to get the expected value, we just sum up the values times the PMF, right? So the sum of y times the probability that y equals y. That would just be expectation of y. The only difference is we make this conditional, given x equals x. That's all this means, that we learned that x was equal to x, and so we condition on that information, right? So it's our best, you know, it's our best prediction of the value of y given this information. Best in a certain sense of minimizing, you know, the square of how far off you are on average. So it minimizes expected squared error. That's the discrete case. Well, let's also just write down the continuous case. So if y is continuous, then the basic definition of expectation would be we'd integrate y times the PDF of y, and now we're just going to use a conditional PDF instead, which we might write as f of y given x, y given x, dy. Okay, and if x is also continuous, just to remind you of how do we get this conditional PDF. Well, the definition of the conditional PDF is completely analogous to conditional probability. That is, instead of a probability, we have the density, but the density of y and x divided by the density of x. So that would just be the joint PDF divided by the marginal PDF of x. So this just says that this equals this because it just says that to get the joint PDF, we could take the marginal PDF of x times the conditional PDF of y given x. So we could also write it this way. And notice that this marginal here, that doesn't depend, this is dy, not dx. This doesn't depend on y, so we could take this out of the integral if we want, or we can leave it there, same thing. So this is just the analog. It's just saying we're using a conditional PDF, and it's defined analogously. So I mean that's how you would compute things using a sum or an integral, but that doesn't yet say like what properties does this satisfy. Okay, so let's let this thing be g of x. That's g of lowercase x equals e of y given big X equals little x. I'm writing as g of x just to emphasize the fact that this, when you compute this thing, because I can't even count the number of mistakes I've seen in these kinds of problems where, I give a problem like this on an exam and then get an answer that involves capital X or capital Y, which you should immediately know would be completely wrong. Okay, because this is the expected value of y. It can't depend on capital Y because you're taking the average of y. So how could that depend on? You can't base that on y, right? That's your prediction of y. You can't use y. Okay, given this information, x equals little x, so we're conditioning on this event, and it can't involve capital X. It can't involve capital Y. It's just a function of little x. It might be a constant. If x and y are independent, then conditioning on x gives us no information about y. So if they're independent, this will just reduce to e of y, which is a, a constant function, okay? But it has to be a function of x, possibly a constant function, okay? So that's just, to emphasize that's a function of x, but that also suggests how to define conditional expectation given a random variable. So we want to define e of y given capital X as g of x, capital X now. So, I mean, this is like, not a complicated looking equation, but conceptually, this takes a lot of thought. And I'll explain it, and I'll explain it more in the next lecture. But really, you just have to take some time to just think about what these things mean. Like, think carefully about it, because there's just so many mistakes you could fall into if you don't fully understand what this notation means. All right, so what this thing means is we have this function of little x, and we replace little x by big X after evaluating it, not before. So one trap you could fall into here is to say, well, g of capital, this is g of little x, g of capital X, then I should plug in big X for everywhere I see a little x, so I'd plug it in there and there. But in that case, you'd be saying e of y given capital X equals capital X, and then you'd say, well, I already knew capital X equals capital X, so that's just irrelevant information that I'll cross out, and you get e of y. That's not what this means. What it means is think of this as a function of little x that you've actually computed. Like maybe it's x squared. I'll just write this as an example. So what it means is if g of x, little x equals x squared, then g of big X equals big X squared. That's all it means. That this is some function of x, and we replace little x by big X after we've actually, actually have our hands on that function. Okay? It's really just a notational trap to think of plugging in the x here. But think of this is some function, you're replacing little x by big X. Notice that that's a random variable. So in particular, e of y given x is a random variable. It's a random variable that's a function of x. It's not a function of y, it's a function of x. All right, so the intuition for that is that I mean, this is the definition, but the intuitive interpretation is that e of y given x, what that means is x is a random variable, but let's pretend that we observed x and we know what x is, and we then get to treat x as if it's a known constant. That's what this says. So it says, assuming we get to pretend that x is known, then what's our best prediction of y? So that's allowed to be a function of capital X. Okay, so that's what it means intuitively. It's not really that different from this, and in fact, when you have a problem like this, you can always, at least in principle, translate it back into conditioning on an event. It's just that the notation gets more unwieldy in this case, and we'll see examples where it's just a lot more compact and convenient to write things this way than always having to revert back to this. But if you start getting confused about what this means, then it probably should revert back to this kind of notation. Okay? So, all right, so let's do a couple examples. So, let's do one with Poissons. So let's let x and y be IID Poisson lambda. So, all right, so suppose we want to find e of x plus y given x. So as I said, if we want, we could first find this given big X equals little x, and then change little x to big X, and you'll get the same thing. But just for practice, let's do this directly using the interpretation I mentioned, that this says we get to pretend that we know x now. All right, so linearity still holds So this is E of x given x plus E of y given x. We can still use linearity. The reason is that conditional probabilities are probabilities, right? So conditional probabilities satisfies all the same rules and properties as probability. But therefore, since conditional expectation is defined in terms of conditional probability, conditional expectations are expectations. It satisfies the same properties such as linearity. So linearity is still true. Okay, now let's just think about what does this thing actually mean. E of x given x, that's easy. That's x, right? What else could it be? I know x, and I want to predict x. I'm going to use x as my prediction. So, okay. It has to be that. Now let's think about E of y given x. X and y, I said they're IID, so they're independent. Since they're independent, that means that getting to know x is of no use at all in predicting y. So that's just the same thing as E of y. So this part is by independence, and this part is x is a function of itself. In general, we'll talk more about this later, but I may as well mention it now. If we have E of h of x, this is true for any problem, not just for the Poisson, so I'm putting it above this. We'll come back to this later, but since it's already coming up. If we get to know h is any function, we get to know x, well then we know h of x. We could just compute it. So E of h of x given x has to be h of x, right? Because we have x, we have h of x, so that's it. No uncertainty about it. Okay, so E of x given x is x. E of y given x is just E of y, so that's just x plus lambda for the Poisson case. Actually, I didn't even use, up to this point, I'm not using anything in particular about Poisson. I'm only using the fact that they're independent. Okay? So that's just an example that shows, okay, we can still use linearity. If we have independence, we can drop the stuff we're conditioning on. And if we have something that's completely known, then we can actually just take it out because it's known. All right, now let's do a kind of a reverse problem. Suppose we were asked to find E of x given x plus y. And, okay, so there's no form of linearity that says this is E of x given this plus E of x given y. And I've seen that mistake several times, maybe in like time pressure type of panic. Just to, linearity is like this. You can't do that here. Okay, so we have to think about what this means. So I'll show you two ways to do this actually. One way is just straight from the definition. We're going to let t equal x plus y, and let's find the conditional distribution, right? Because what this says is we get to know the value of t, and then we use the conditional distribution rather than the right? Without this, it would say just the unconditional, right? What's the expected value? We know it's lambda. But given this information, right, treating t as known, then we need a conditional PMF. So find the conditional PMF. Okay, so this is similar to other problems we've seen, where but let's just compute it for practice. We need the conditional PMF. We want the probability that x equals k, let's say, given that t equals some number, let's say n. Those are just dummy variables here. I'm just saying find the conditional PMF. That is, what's the distribution of x given that we know t, okay? So by Bayes' rule, that's just the probability that t equals n given x equals k times the probability that x equals k divided by the probability that t equals n. And that's actually an easy calculation because this is another example like that plugging in thing with the two envelope problem. T is x plus y, so we're going to plug in x equals k, and so we know that y equals n minus k. But then in this case, we do get to cross out this information at that point because x and y are independent. This would fail if they're not independent. But in this case, x and y are independent, so really this is just the probability that y equals n minus k, probability x equals k, divided by the probability that t equals n. And, sorry, we're going right to left here. Let's just write what is this here. Y equals n minus k, just straight from the Poisson, right? E to the minus lambda, lambda to the n minus k over n minus k factorial. X is also Poisson, e to the minus lambda, lambda to the k over k factorial. And in the denominator, we know that the sum of independent Poissons is Poisson. So this is going to be Poisson of 2 lambda in the denominator. So we know that's e to the minus 2 lambda to the n divided by n factorial. Okay, and if we simplify this, we get a very familiar looking distribution, right? What distribution is this? Binomial. Notice e to the minus 2 lambdas cancel, right? And this power of lambdas cancel, right? There's lambda to the n over lambda to the n. We just have a 1/2 to the n here, right? And this thing, n factorial, put that on top. That's just n choose k. So this thing, I'll simplify it one more step. It's just n choose k, 1/2 to the n. That's just a binomial. Okay, so what we just showed with that Bayes rule is that x given that t equals n is binomial with parameters n and 1/2. So now let's use this to get the conditional expectation. So what that says is e of x given x plus y, but let's first do the case of conditioning on an event. So we're given t equals n. Well, that just says given t equals n, it's no longer Poisson, now it's binomial. The expected value of this binomial is just n over 2. So in the other notation, this is conditioning on an event, right? But if we want to condition on t instead, e of x given t, then all we have to do is replace this n by t, just according to that definition there. So that's going to be t over 2. So it says that if we get to know the total, then our best prediction is 1/2 the total. That's actually a pretty intuitive result, right? That we get to know the total of x and y in their IID, and we want to predict the average of one of them. Well, if I told you the total is 100 and their IID, you'd probably guess that they reach 50, right? That would be a reasonable guess. So that's a mathematical proof that's kind of the correct guess. That's one way to prove it. Here's a way that I like even more, is to notice the symmetry. E of x given x plus y equals e of y given x plus y is true by symmetry because they're IID. This is always true with IID. That doesn't assume anything about the Poisson. Let's add these two things. E of x given x plus y plus e of y given x plus y. By linearity, that's e of x plus y given x plus y. But e of x plus y given x plus y is x plus y, which is t. So I added something plus itself, and I got this, so that immediately implies the same result. E of x given t equals t over 2. And this didn't use anything about the Poisson, so that's actually a more general result. All right, lastly, let me just mention one key property that this notation gives us. We'll prove it next time. So this is called iterated expectation, or it's also called Adam's law, for reasons I'll tell you next time. This is the single most important property of conditional expectation, so it's good to be aware of it now, and then I'll talk in detail about it next time. It just says As I said, e of y given x is a random variable, so we might want to know what's the expected value of that random variable. Well, if you do e of y given x, you get e of y. And this is closely related to the law of total probability. It's like, in a sense, it's a very compact way of writing the law of total probability. Extremely useful fact. All right, so I'll see you on Wednesday.